So we've been talking about trends in the periodic table. So the next one we're going to talk about is ionization energy, and so of course we need to define what is ionization energy. We abbreviate this IE. Ionization energy is the energy needed to remove an electron from an atom or an ion, and that's measured in the gas state. So this energy is always positive because atoms and ions do not just give up their electrons, you have to pay them. So energy is like money, you have to give energy to give money to the atom for it to give you its electron. So we can write a chemical equation to represent this. Here, M representing the atom in the gas state, you add the ionization energy, and you're going to remove one electron, and that gives you a positive 1 ion. So IE1 stands for the first ionization energy, the energy to remove the first electron. From that ion with a positive 1 charge, you can add more energy and remove a second electron. That's called the second ionization energy. And now we've got a +2 ion. So the trend in the first ionization energy, decreases as we go down a group. So this trend is opposite of atomic size. Here on this graph, we can see the noble gases, helium, neon, argon, krypton, xenon. The ionization energy goes down as we go down the group. It becomes easier to ionize the atom. At the bottom here, we have group 1A, and the trend is not as dramatic here, but the ionization energy decreases as we go down a group. The reason for this is the valence electrons are farther away from the nucleus. Coulomb's law tells us that the energy involved in the attraction between these opposite charges is proportional to Q1, Q2 over R. So if the distance between the charges is greater, the attraction is less and it requires less energy to remove. As we go across a period, so from lithium to neon across a second period on the periodic table, we see that the ionization energy increases dramatically. It's not a completely smooth line. There's a couple of zigzags in here, and we'll talk about those in a minute. Any questions? So as we go across, why is the ionization energy increasing so much? It takes more energy to remove an electron. Why? What's the trend in atomic size going across a period? Gets smaller. So R is becoming smaller, so that's going to increase the energy. But the big thing is the effective nuclear charge increases. So Q1 might represent the charge on the electron, Q2 might represent the effective nuclear charge. As that increases, the amount of energy necessary to remove that electron increases dramatically. There's a different kind of a graph showing trends in ionization energies with ionization energy as a vertical stack. And so we see that the trend is that they get smaller as we go down any particular group, and they get larger as we go across. So we should be able to answer questions like this. On the basis of periodic trends, determine the element in each pair with the higher first ionization energy, if possible. So we need to look at the periodic table to answer this. We need to find tin and iodine. So on that little section of the periodic table, there's tin and there's iodine. Which one has the larger, the higher first ionization energy? Iodine. The trend is as we go to the right, the ionization energy becomes larger. So iodine has the higher first ionization energy. Another way to remember this, what kind of an ion does tin form? A cation or an anion? It's a metal, right? Tin forms cations, right? Positive ions. And what kind of ion does iodine form? A negative. So Have we ever discussed an I+ ion in class? No. They are very rare. They really just don't exist because iodine has a high first ionization energy. Tin, we see tin 2 and tin 4 frequently. Tin loses its electrons much easier. It has a lower ionization energy. So you can use that to kind of help you remember the trend here. Let's look at calcium and strontium. They're over on the left side in the alkali metals. We have calcium, and here's strontium. Higher ionization energy. Calcium. As the trend is, as we go down a group, the ionization energy decreases. Calcium is a smaller atom. The electrons are closer to the nucleus. It's more difficult to remove them. How about carbon or phosphorus? Not really possible. So these are at a diagonal, and those can be tricky. We have opposing trends. If we go across, ionization energy increases, so that would say phosphorus is larger, higher ionization energy. But the trend is as we go down, the ionization energy decreases. So we could say not possible. What if we were forced to choose? I would choose carbon, yeah. We haven't seen any ions of carbon, have we? Positive or negative. What kind of ions of phosphorus have we seen? Negative. It becomes a negative ion by gaining electrons, not losing them, right? Actually, I wouldn't go with carbon. I just talked myself out of that. Phosphorus is probably less likely to lose electrons because it becomes a negative ion. These sorts of questions will be on the 4th exam, and they will make you crazy, okay? And so really you need to talk to yourself and reason it out, because we just said carbon and then I just talked myself out of it. So if we had to choose, I would choose phosphorus with higher ionization energy. Okay, fluorine or sulfur? Fluorine. As we go across, ionization energy increases, so that says fluorine. As we go down, it decreases, so that also says fluorine. Any questions? Yeah. Why did I say I would choose phosphorus? Because of the sorts of ions that we actually see. So phosphorus forms a 3- ion, meaning it gained 3 electrons. That tells me it's probably going to require more energy to remove electrons because it's just not going to like that. For carbon, we really haven't seen any ions, and so it seems like it's kind of stuck in the middle. It's not going either way. So I would reason that it's easier to remove an electron from carbon than from phosphorus. That would be if I was forced to choose. Any other questions? Of course, there are exceptions to these trends. We see an exception between group 2A and 3A in the periodic table. Boron has a smaller ionization energy than beryllium, and that's opposite of the trend. What's happening there is that boron is losing a 2p electron, which is less stable. It's a slightly higher energy sublevel, and beryllium is losing a 2s electron. And so it requires more energy to remove that 2s electron than the 2p electron. So we can look at orbital diagrams for these two guys. I'm going to do beryllium over here. There's 2s and 2p. That's beryllium. And over here, 2s and 2p. This is boron. How many valence electrons does beryllium have? What group is it in? Group 2? Beryllium? Yeah. Be? He's way over there. 2 valence electrons, right? So we put those in the orbital diagram. We got one here and one there. Boron has 3, right? It's the next one over. So we've got 2 here in the 2s orbital, and the third one is in the 2p orbital. This is higher in energy. Removing this electron is easier than removing one of those. And so we see this glitch in the trend. We see another one between group 5A and group 6A, between nitrogen and oxygen. Here's the orbital diagram for nitrogen and one for oxygen. So for oxygen, we're removing this electron that had to pair up. Both of them are losing a 2p electron, but this one had to pair up. And so that's a less favorable situation than this one who has his own bed, right? So oxygen has a lower ionization energy than nitrogen. We can explain these things. I don't necessarily expect you to regurgitate this on an exam. Successive ionization energies, this is removing 1 electron and then 2 and then 3 and then 4, comparing the energies required for that. So looking at sodium, the first ionization energy is 496 kilojoules per mole. The second ionization energy is almost 10 times as large. It's a huge jump. And then the third ionization energy is 6,910. Well, how many valence electrons does sodium have? 1. So when I remove 1 electron, I've removed all of the valence electrons. When I remove the second electron, now that is what used to be a core electron, right? Closer to the nucleus, having a higher effective nuclear charge is going to be a lot harder to remove that one. How many valence electrons does magnesium have? 2. So those would be in the 3s sublevel. When we remove 1, requires some energy. Removing the second one is about twice as much energy because you're pulling electrons off, right? Double. The third one is huge because you've lost the 2 valence electrons and now you're getting into the core electrons. And so there's this huge jump. We get a big increase when the first core electron is removed. Any questions? This is a table showing successive ionization energies for different elements. And what we see here between the blue and the pink, a huge jump, and that's because this is where the first core electron is being removed. And so if you look at the trend here, it's going up every time, but when you get into the core electrons, that's when the big leap, big increase comes.